Hello and welcome to the second part of Lecture 3 in EEE 23, Electromagnetics 1 for UP EEE students. We'll start where we left off on Gauss law. So just a recap, Gauss law, as we have talked about it, when we want to solve for an unknown electric flux density, we usually take advantage of symmetry to be able to solve our flux density. But how about for uh, distributions that are not exploitable with symmetry? How do we solve that? So we can't really choose a surface in this case. For example, a heart-shaped uh, charge distribution. We can't really choose a surface that can enclose it such that it has symmetry. Okay. How do you solve this kind of problem? Okay. And instead of looking at it at a larger scale, let's look at it in a smaller scale. Consider a differential volume that encloses a point P. Okay, so this volume is very small. So let's consider then the Cartesian coordinate system for now. This volume is very small and it's a rectangular prism with sides delta z, delta y, and delta x. Okay, so at the point P, we have an electric flux density defined by this equation. It has a value dx naught at the x component, dy naught y component, and dz naught your z component. If we apply Gauss law to this very small volume, so invoke Gauss law, we have the closed surface integral of your electric flux density dotted to your differential surface, which is equal to the total charge enclosed. Okay. Now this surface has 6 sides. Okay. So if you can see, it's there are only 6 sides here, and in these cases, the direction of the surface area vector is constant at each side. Okay? For this side, it's ay. Sorry, there you go. Maybe that's better. At this side, it's ax. Okay, let me just clean that. At this side, it's ax positive. At the back, it's ax negative. Here, it's ay. Here, it's negative ay. From here to the top, positive az. And finally, bottom, negative az. So that is the breakdown of the closed surface integral of this area right here, this volume right here. And it's the integral of the front, back, left, right, top, bottom. Basically, just solving for the flux, total flux at the front, total flux at the back, total flux at the left side, total flux at the right side, total flux of the top, and total flux of the bottom. You just add them all up, you get your charge equal. You get your total flux, okay, and that is equal to the charge enclosed by the volume. So that's Gauss law. Okay. Now let's look at one component of the flux. Let's look at the front component. So that's just basically the flux density at the front. So it's right here, okay, some distance away from P, dotted to the total area of this face right here, which is the front. So in this case, it's actually assumed that the flux at each point is constant. Okay, so the flux at each point on this area is constant. Why is that? Well, actually, since this is a very small volume, we can approximate that there is no change in flux in the front. Okay, so how do we get the flux at the front? Okay, If you look at this equation, so we let D front have an X component, Y component, and Z component dotted to your differential surface area, which is delta Z times delta Y, and the direction of that delta Z and delta Y of that differential surface is along positive AX hat. Sorry. Okay. So if we get the dot product, the Y and Z components won't matter, and what we'll be left with is uh, the X component of your differential, the X component of your electric flux density times the area of the front rectangle. Okay. So now let's get dx front. Dx front is equal to this equation right here. Remember, dx naught is the flux at the point P. Delta x over 2 is the distance between the point P and the point at the center of this area at the front. Okay, so it's this point. Okay, so that's the distance between them times the rate of change of the flux, the x component of the flux with respect to x. So how is this equation valid in the first place? We actually we have to actually go to the definition of partial derivatives. Okay, so it's actually something like this. Since your x component of your electric flux density is a function of xyz. How did this happen? Well, since your electric flux density is a vector field, each of its component changes value with respect to the point in space. So this flux density can be derived with respect to x. We can take the derivative of this with respect to x. So this actually means how much this electric flux density changes with respect to x. And by definition of your derivative, this is actually just equal to the change in your electric flux density, x component, and divided by the change in x, which can be written as this is your dx front, sorry, minus your dx naught. Okay, and this delta x is the distance between them. Distance between them is 0.5 of the given delta x. All right. So we can now solve for dx front. Dx front, we just cross multiply. So dx front, we just cross multiply uh, the term 0.5 delta x. So that's there you go. And you just transpose this term to the other side right here. All right. So that is your dx front, and that's what happened in this slide right here, specifically in this equation right here. So this equation is still valid, and that is the flux, the x component of the flux at this point right here. So the total flux on the front side of your differential volume is equal to this equation right here. Okay. So similarly, if we look at the back part, so this is the back part that we'll consider. From the point here at the back part, you have a vector negative ax hat. Okay. So again, there's a flux density at the back, and that is defined. We let it have an x component, a y component, and a z component. But since we're looking at the direction of negative ax hat, these two won't matter, and basically the flux at the back side of your rectangular prism is equal to this equation right here, or this expression right here. And we have dx back equal to, similarly, you can get the dx back using the definition of your partial derivative like this. And when you plug in the values, it becomes negative delta x over 2. Why? Because from this point, the change between this point and this point is negative, since at the backside, the x coordinate is more negative than the front than the point in the middle. Okay, so that is negative delta x over 2 times uh, the partial derivative of your x component of the electric flux density. Okay, so finally we have the back. Just substitute this here. Okay, we get this expression. So this is the final expression for your uh, flux density, sorry, total flux at the backside of your differential volume. So we add this to the front. So we add this to the expression that we got earlier here. If we add them, dx naught will cancel with dx naught here. And what will be left with this expression right here. Partial derivative of your x component with respect to x times delta x, delta y, and delta z. Similarly, if we analyze the right and the left, we get the partial derivative of the y component with respect to y times delta x, delta y, delta z. If you add the top and the bottom, you get the partial derivative of z with respect the z component with respect to z multiplied by delta x, delta y, delta z. So if we add them all up, you'll get this expression right here times delta x, delta y, delta z. Or we can let this be equal to delta v. So delta v is the small volume. So the charge enclosed by a small volume delta v is approximately equal to this. Okay, this term in within, it's just a function of the components of your electric flux density. Okay, so delta v is a very small volume. So just a note, that is a small volume. If delta v is large and it's very large, then this equation will not work. Okay, so for example, we have the charge in a volume that is very small, 10 to the minus 9 cubic meters. The electric flux density is this equation right here. Oh, there you go. So first, you need to evaluate that using the expression that you got earlier, partial derivative of the x component with respect to x, partial derivative of the y component with respect to y, and uh, partial derivative of the z component with respect to z. Okay, so just get the derivative here, here, and here, and add them all up. So this, you take the derivative with respect to x, you get this expression. This, take the derivative with respect to y, you get this expression. And this, you take the derivative with respect to z, you'll get this expression. These terms will cancel each other out, and you'll be left with this. So basically, it's just 2. What does this mean? It's constant. Therefore, at any point x, y, z, the charge enclosed by a very small volume is equal to 2. Okay. If we multiply it by the actual volume, we get the total charge enclosed by that small volume right there. So you'll get this this final answer right here. So it's 2 nanocoulombs. So you can visualize it like something like this. Okay. So this small volume is 10 to the minus 9. Okay. So 10 to the minus 9 meter cubed. Okay. And basically the charge inside is 2 nanocoulomb. So there's a charge inside here. I don't know what shape it is, but it has the total is 2 nanocoulombs. Okay. So now this term is actually The term inside, the weird term inside, it's actually called the divergence of your vector field D. The formal definition of which is this. So if we divide both expressions by delta V, so we get this divided by delta V, and we take the limit as delta V approaches 0, okay? So that means we're enclosing this point into a very small volume. We're shrinking the box and basically trapping the point P inside it. Okay? So we're shrinking the box, trapping the point P inside it, and you'll get this expression right here. And it's called the divergence of your vector field D. Formal definition: for any vector field A, the divergence of A is defined as this expression right here. Okay? If you take that definition and apply it in cylindrical and spherical coordinates, you'll get these expressions right here. So don't bother if you don't want to do tedious mathematics on this. Just accept that this is the definition of the divergence for cylindrical and spherical. Otherwise, if you're up for it, you can use the formal definition. Okay, let A be a vector expressed in cylindrical or spherical, and just roll with it in terms of ds. Just let ds be the let ds be your vectors, differential surface area vectors in cylindrical and spherical. Okay, so the mathematics there is tedious, and just trust trust that this actually works. Okay, so now if we look at it in terms of electric flux density given a small volume delta V again, or if we divide both sides by delta V, we get this and this equal to the divergence of your electric flux density B. Getting the limit as delta V approaches 0, again, this expression right here. That means this expression, we also let delta V equal to 0. We let delta V approach 0. This expression becomes a very small point, and it has some charge at that very small point there. Okay, so very small point has a differential volume, and because of that, it has some form of differential charge. Okay, so kind of like differential charge with respect to volume, or coulombs per meter cube. And that's actually your volume charge density. Basically, the divergence of your electric flux density is equal to the charge density in space. Okay? So it's amazing how something so big like having a Gaussian surface, generally a weird Gaussian surface, okay, so it's not really a perfect cube, but you get the point, and has some form of distribution that you don't know, uh, how it is shaped, okay, can be generalized into something smaller and became this simple equation right here. Okay, so how do you interpret some equation like this? What is the divergence in the first place? Okay, so the divergence is actually a measure of how much flux is going out from one point. Okay, so how much flux is going out of one point? So you take note of that. So basically, if this is your volume charge density, so at this point P, if the divergence at this point is positive, then at this point there are more flux going out of the point than the number of flux lines going into the point, making it a source. Remember then that for a positive charge, okay, for a positive charge, the electric field is being emanated from the positive charge. Okay? So that means if your volume charge density is positive, the divergence of your flux density is positive, it means the net flux or the total flux is going out of that point. Okay? There are more flux lines going out of that point than going into the point, or there is a positive charge on that point. Or basically the net charge on that point is positive. Inversely, if it's negative, we know that the electric field is going into the negative charge. Like the negative charge actually absorbs absorbs electric field. So if you have a point with more flux lines going into the point rather than going out, okay, so there's more going in, the divergence at that point is negative, or your it's kind of absorbing your electric flux. This is called a sink. Okay? It absorbs more than it's letting it that than what it's blowing out. Okay, so that means there's a negative volume charge density in that point. Okay, there's a negative volume charge density in that point, or basically the divergence is less than zero. Okay, so that's how you interpret divergence of a vector field. So some remarks. This is actually Maxwell's first equation, also known as the point form of Gauss' law. Conversely, if we look at the larger part or the bigger part, instead of looking at finer points, we look at the bigger part. The Gauss law is actually the integral form of this equation, which is Maxwell's first equation. Okay. So let's go to an example. Determine the divergence of D in the region about a point charge Q located at the origin. So knowing that the electric flux density is equal to this function right here, just get the divergence of this. You'll get this expression right here. So since it doesn't have a theta component and phi component, this will just be 0. And you'll be left with this equation right here. So if you get the derivative of this with respect to r, it's 0. Since if you multiply this, the r squared will be cancelled. Q is constant, 4 pi is constant. Derivative of a constant is 0. Therefore, the divergence of this uh, electric flux density is 0 for r not equal to 0. That means that the charge density everywhere is 0 except the origin, where it is infinite. Okay? Since it's a point charge, the volume is 0. So the charge density is equal to Q over 0, which is equal to infinity at that point. Okay? Another example. In a region in free space, the electric flux density is found to be this expression. So, how to plot that? Well, the plot looks something like this. So, yeah. There you go. At this point, so this is D and this is Z. At this point, the flux density is equal to 2 rho naught D. Okay? So I can let you verify that. Anyway, this is the plot of the magnitude of your flux density. So everywhere else it's 0. So using the divergence of D, find the volume of the charge density as a function of its position everywhere. Right? So the divergence of D is equal to this expression. Since it doesn't have an x component and a y component, it will just be left with this. And if we're looking at this region, that is this equation right here, take the derivative of this with respect to z, you'll just be left with rho sub 0, or rho naught. Similarly, if you look at this region, it's this expression, take the derivative, it's negative rho naught. Okay, so again, there's no x and y component. Finally, anywhere else, since the expression here is 0, this is 0, 0, 0, you'll be left with 0. Okay, so the total expression is this. Basically, it means that if we look at the region, in the z-axis at least, so in the z-axis, wait, let me fix that. Okay, that sucks. But anyway, so z-axis, this is your charge density. Then at this region, it's positive. Then it's negative in this region. Okay, so anywhere else it's 0. So this is the graph of it, right? So that's the charge density for the given electric flux density. Okay, so part 2 ends here. What to expect in the next parts? Well, let's formally define divergence in terms of an operator we call del or nabla. Okay. Okay. So we'll end the part 2 here, and part 3 will be about the vector operator and what we call the divergence theorem. Okay? And that's the end of this lecture. Hope you learned something new, and I'll see you again soon.